Hey everybody, this is the first of a series of video lessons for regular chemistry covering the topic of stoichiometry. Stoichiometry is a really big word, but it doesn't need to be that difficult of a concept. In fact, it's nothing more than simple dimensional analysis. But what makes stoichiometry unique is that it's dimensional analysis revolving around a balanced chemical reaction. So the most important part of stoichiometry and what makes stoichiometry is the balanced chemical reaction. Here's an example of a balanced chemical reaction, and I'm going to use this one reaction to do all my examples here today. The way these video lessons are designed is to start with single-step stoichiometry and then add steps until you get to the largest type of stoichiometry problem, which is the three-step stoichiometry problem. So this first video lesson is going to cover one step, or also known as mole-to-mole stoichiometry. Now, in order to do mole-to-mole stoichiometry, we need to generate a conversion factor, which is just a tool that we're going to use to do the dimensional analysis with. That dimensional analysis tool, or that conversion factor, is known as the mole ratio. Now, you might be wondering what the mole ratio is, and, well, I'm about to tell you. If you look at the balanced chemical reaction, you see that the coefficients out in front of each of the reactants and each of the products has a number in front. Now we use these numbers and we represent them as molecules of N2 or molecules of H2 or molecules of NH3. But in order to do stoichiometry, you treat the coefficients not as individual atoms or molecules, but you treat the coefficients as moles of each of the reactants and products. And so this reaction happens in a 1:3 ratio. For every 1 nitrogen, you use up 3 hydrogens. And as a result, you produce two NH3s. So in the mole ratio, we're going to treat the coefficients as moles or whole quantities of these molecules rather than individual particles. And when you do that, you can describe a chemical reaction in terms of its mole-to-mole ratio. So scrolling down to give myself a little bit more room here. Usually, you'll start with a number of moles, and you will be asked to solve for a number of moles of a different part of this reaction. Here's a problem that I present you with. When we start with 1 moles and solve for another. So in this problem, I actually start with the answer. How many moles of H2? So I'm going to be solving for moles of H2. If I start with 5 moles of N2. Now, the tool that I'm going to use to solve this is the balanced chemical reaction up here. And at first glance, you might be a little confused because you see 3 things in this chemical reaction. Some chemical reactions have 4 things or 5 things. But in stoichiometry, you can only really deal with 2 things. One thing you know and one thing you're trying to find. Any other part of the chemical reaction is assumed to be extra information, and we just don't use it at all. So you really focus in on the 2 things, what you know and what you're trying to find. Now I know the N2 and I'm trying to find the H2, and I really don't care about the NH3 at all. Stoichiometry focuses on just 2 things at a time, what you know and what you're trying to find. So here's how this problem works. Just like every dimensional analysis problem, we begin the problem with a number and unit given to us in the problem. And so I will begin with 5.0 moles of N2. Now it's important to label the moles of what? Moles of N2, because you're solving for moles of H2. So I see a lot of students get kind of lazy when it comes to labeling their units here, but now it's even more important that you label your units properly. When I write out moles, I write moles of what? Moles of N2. Because down here, when I multiply by a ratio, I'm going to put moles of N2 on the bottom because I need those 2 units to line up across from one another. I need them to be diagonal so that they cancel each other out. Now on top, I'm going to put moles of what I'm looking for, which is H2. This right here, and I'm going to outline it, is what is known as the mole-to-mole ratio. Right here. It is the coefficient of the chemical reaction, and I'm going to put the numbers in. So what's in front of the N2? Well, there's a 1, and what's in front of the H2? There's a 3, and I've just generated the mole to mole ratio. So if I have 5 moles of N2, then I'm going to need 5 times 3 or 15 moles of H2 to react with it. So what the mole to mole ratio allows us to do is that it's a tool to convert between moles of one thing and solve for moles of a different thing using the balanced chemical reaction. So I've added this little note underneath the mole ratio. Its job is to convert from moles of one thing to moles of another. Normally I call it moles of substance A and moles of substance B, where A is what you know and B is what you're trying to find out. So in the problems that I will be presenting to you, and in the examples that I'm going to show you, you're going to have moles of what you know, in this case moles of N2, and you're going to be trying to solve for moles of what you're trying to find, which is H2 in this case. Now, in this example, I compared the two reactants. But let's do another example where I'm going to do mole to mole ratio again, but I'm going to be using maybe one of the reactants and one of the products. So let me scroll up here so that I can give myself a little bit more room. So I rewrote the chemical reaction because I need these coefficients in order to do my mole to mole step. I added a 1 there in front of the N2. Here's the problem. How many moles of NH3 can I make, so I'm solving for NH3 this time, using 2.25 moles of H2? And in this particular problem, I can cross out the N2 because I don't need it. It's extra information in the chemical reaction. I need the N2 in the reaction to balance the other two substances in the chemical reaction, but when it comes to actually doing the math, it is not included as part of the math. So I set up this problem, once again, using dimensional analysis like I did before. So I start with 2.25 moles of H2, 2.25 moles of H2, and I divide by 1. I multiply by moles of H2 down here. Remember, the dimensional analysis says that the moles has to cancel the moles. Now in the top, I'm going to put moles of the NH3 because the question asks how many moles of NH3. As I'm developing my skills, if I'm starting this process, which many of you are doing for the first time, I would say that it is good practice to actually underline what you have in the problem and try and circle what you're trying to find. So I'm underlining 2.25 moles and circling moles of NH3, which pretty much tells me or helps me set up my game plan. Now what I need to do is put in the coefficients from the balanced chemical reaction, and I need to put them in the right spot. And since NH3 is on the top of my dimensional analysis, I put 2 NH3s next to it. And then the H2, which is on the bottom, and I just simply pick the coefficients out of the balanced chemical reactions, and I put 2 on top and 3 on the bottom because I'm trying to get rid of H2 and solve for NH3. So when I put this into my calculator, I get 1.50 moles of NH3. Now your calculator just says 1.5, and I added the 0 on the end because I needed 3 significant figures. So I'm going to do one last example involving the same chemical reaction. I'm just going to slide down so that I have a little bit more room to write. Once again, I'm going to write out the balanced chemical reaction. So I wrote down the balanced chemical reaction, and I also jotted down this practice problem. If I want to produce 4.75 moles of NH3, and then that's my starting number, how many moles of N2 do I need? So again, as I'm developing this skill, I underline what I have and circle what I'm trying to find. So I start with the 4.75 moles of NH3 over 1. And I'm going to multiply by moles of NH3 on the bottom and moles of N2 on top. What about the H2? Well, it doesn't matter because I can only compare 2 things at once in a stoichiometry problem. Even if there's 3 or 4 things in a chemical reaction, only 2 things can be compared, what I have and what I'm trying to find. So I have 4.75 moles of the product, and I'm trying to find how much N2 does it take to get that much. And so I used the balanced chemical reaction and the coefficients once again in order to do that. So my N2 is 1, so I put 1 mole of N2 on top and 2 moles of NH3 on the bottom. So now I can do the math. 4.75 divided by 2 is equal to 2.375. Now, I need to round that to the significant figures that match the initial number in the problem, and this is 3. So my answer rounds up to 2.38 moles of N2. And that's my final answer. So as I finish up my conversation about one-step stoichiometry, I want to jot down a couple of key points here, almost as a summary. And the first thing I want to talk about is the flowchart that I like to teach stoichiometry with. This is going to be our framework, which I'm going to refer to many, many, many times over the next couple of weeks. The essence of stoichiometry, what makes stoichiometry, is the mole to mole conversion. So if you have moles of substance A and you want to convert to mole of substance B, then you are doing stoichiometry. So the middle of the flow chart, and I'm focusing on just one part, the middle part right now, is the mole to mole step. Now, the conversion that I use to do the mole to mole step is called the mole ratio. Similar to the flow chart that I created for the last chapter for the molar conversions, this now is a new flow chart which has the middle part of mole to mole ratio. So moles of A to moles of B, moles of what you know to moles of what you're trying to find, you use the mole ratio. The mole ratio uses the balanced chemical reaction in order to generate that conversion. Now, as we build stoichiometry, we're going to add things to the front side and the back side of this flow chart, but for now we're focusing on just the middle aspect, the mole to mole step. Sometimes, depending on your chemistry teacher, your chemistry professor, your chemistry textbook, this step is referred to as the mole bridge because it bridges the two sides of stoichiometry, from what you know to what you're trying to find. It is the link between two halves of the problem. I just call it the middle step. So I'm going to leave you with a couple of things to remember when doing all stoichiometry problems, not just mole-to-mole stoichiometry problems, but all stoich problems. You need to have a balanced chemical reaction. The reaction has the coefficients, and the coefficients generate the mole ratio. Without the balanced reaction, you cannot do stoichiometry. The next thing to remember is that stoichiometry only can compare two parts of a reaction at once. If you have multiple parts in a chemical reaction, the other parts don't matter. You can only compare something you know with something you're trying to find. Those are the two parts. And it's important to identify those in the wording of the problem. And if you need to, identify them by circling and underlining like I showed you in our last examples. Finally, it's important to fully label your units when you're showing your work. Don't just write moles, but write moles of what? If it's a compound, write the compound's name. If it's an individual atom, just write out the atom symbol. But fully means not just the unit, but also the unit of what? Moles of sodium, moles of potassium chloride, moles of carbon tetrachloride. Whatever it is, fully label it. And also fully label your answer as well, moles of substance. Well, friends, that takes care of this first video lesson on single-step stoichiometry. There will be more in the series of stoichiometry video lessons. Thanks for listening.